honored to have Craig Boutilier with us, and it's our second talk of the day in this very room with an expert in probabilistic and statistical reasoning. Craig goes beyond that to also be an expert in planning and representation and Markov decision processes, partially and fully observable, and lots of other things. So welcome, Craig.
Great. Thanks a lot, Peter. It's a pleasure to be here. It's not often one gets to meet with the brain trust behind, responsible for a piece of software that you use more than anything else in your life. So that's fantastic. And I'm really looking forward to having the chance to chat with some of you folks to talk about the challenges. I think the research challenges that you're facing are probably some of the most intriguing and provocative on the planet these days. So I'm really looking forward to the rest of my day and a half here. So before I get into my talk, which is on, as you can see, regret-based preference elicitation and mechanism design, let me just say a couple of words about myself. As Peter mentioned, I've done a lot of work in Markov decision processes, both fully and partially observable. Generally speaking, I'm interested in any problem that has to do with decision-making or optimization under uncertainty, and its many and various guises. And that includes game theoretic and economic models more recently, and it's something that I will say a few words about in the talk today, depending on how time goes. In particular, over the last, say, 3 or 4 years, a lot of my work is focused on the problem of preference elicitation, and that actually does relate to mechanism design in ways that I hope will become clear in a couple of minutes. Real key question is why mechanism design? What is so important? Why preference elicitation? What's so important about this problem? Well, we in AI, when we think about decision-making or decision-making under uncertainty, we usually have in mind that we're making a decision on behalf of some individual or some organization. We're doing something for somebody. One way to think about it is that we want to match individuals to products that they desire, information, services, other individuals, or even when you're thinking about planning, we want to match them to the appropriate courses of action or specific behaviors that they would find desirable. But of course, decision-making for me means optimization. Optimization means having some objective function. The key question is, what is that objective function? And obviously, if we're acting on behalf of somebody, that objective function needs to reflect the user's preferences. Okay? And this is what I like to call the preference bottleneck in AI. In order to make decisions on somebody's behalf, we have to know something about their preferences. Okay? So a lot of the work that I've been doing over the last couple of years, some of it's been focused on preference elicitation. A lot of it, and this is what I'll be talking about today, deals with the problem of preference assessment, actually more broadly speaking. Either direct assessment, indirect assessment, so the sequential or the one-shot assessment of individual or organizational preferences, in particular in problems that I view as hard optimization problems, combinatorial optimization, stochastic, sequential optimization problems, things of that nature. And a key question that guides most of what I do is the following. What preference information is most relevant to the task at hand, and is the cost of assessing or eliciting that information, does that outweigh the value of the information itself when it comes to making object-level decisions? Okay? I hate these kind of box and arrow diagrams, but I just want to flash this briefly to give you a sense. I'm going to be talking today about direct preference elicitation, where we ask users specifically questions about their preferences in various forms. But when I think about preference assessment, I have a much broader view. In particular, if we have some agent that's making decisions on behalf of a user, possibly a stream of decisions over time, there are a number of things at any point that we can do in order to assess the user's preferences. We can explicitly ask them queries. We can sit back and passively observe how they act, exploiting the notion of revealed preference, going back to decades-old work in economics. We can be passive, but let me call it semi-passive. We can manipulate somebody's environment to find out how they react and get information about their preferences that way without explicitly asking them questions. Okay? And of course, we can take various decisions on their behalf and see how they react, see if they're appropriate or not. Okay, we can rely on the information, the preferences of other users, as one might in a collaborative filtering setting, and so on and so forth. So there are a lot of different modes of preference assessment, and in terms of my overriding interests, it's to develop agents that can do all of this and integrate all of these various sources of information. Just to give you a sense. Here's a project. Let me just click on this. There we go. The project that I'm involved in with some collaborators in occupational therapy in some of the hospitals in Toronto. It's called COACH. This is a prompting system for patients with Alzheimer's, with moderate to severe dementia, who have a very difficult time getting through even the simplest activities of daily living, such as washing their hands. I've got the audio off here, but the system is actually prompting this gentleman to do various things when it appears that he's confused. So the question here is, when should we prompt somebody? How should we prompt them? When should we intervene and call the caregiver to come take over and make sure that the user can get through the task? Okay? So why do we view this as, where does preference assessment come in here? Well, in fact, there's a very difficult preference assessment problem. We solve this. We have this great big POM-BP that we solve in order to do the prompting. But the difficulty is assessing the reward function. Dynamics are easy to learn. There are probably 1,000 people in this organization, in this company, that could tell you exactly how to learn the dynamics of such a process. But when it comes to assessing, the reward function in an MDP or a POM-DP, we've got real difficulty here because caregivers cannot articulate what it is that we should be doing and why over this temporal stream of events. Okay, so here we're looking at problems, and a problem where we have to rely on indirect assessment by looking at caregiver behavior, by looking at by having them critique the policies that we produce, and so on and so forth. Okay. Let me skip this just in the interest of time. Another problem that I'll talk about, which involves direct preference assessment, and I'll get into a little bit of detail here because I'll be talking about elicitation methods for this problem specifically. This is a problem of winner determination in combinatorial auctions. So I don't know how many people here are familiar with what goes on in the sourcing or procurement world these days, but expressive bidding in auctions has become very, very common in areas like sourcing, logistics, procurement, and things of that nature. So rather than having a supplier say, I will provide you with a particular good at a particular unit price, bidders can now package up what they offer to a purchaser and say, look, I can offer you A, I can offer you A at a certain price per unit, but if you give me so much volume, I'll actually discount the price per unit by 25%. Or I can give you A at this price, but if you also let me provide you with B, I can discount what I give A to you for, and so on and so forth. The basic idea is that if we've got expressive languages that allow these package bids, various side constraints, discount schedules, and so on, we allow bidders to directly express their utilities or their cost function, thereby leading to greater economic efficiency. Of course, this degree of expressiveness means that solving what's called the winner determination problem, given a set of these bids, how should one allocate one's business, it now has become, rather than a simple problem, it becomes a very difficult combinatorial optimization problem. But companies such as CombinaToral, a company that I do a little bit of advising for, have been developing techniques that allow one to determine the least cost allocation of business to bidders in very robust ways for very, very large procurement problems. So that's great. Where does preference elicitation come in? Well, obviously, having bidders provide express their cost function can be viewed as a form of preference elicitation. But even the bid taker or the purchaser exhibits complex preferences over the allocations. So we might imagine that Joe here offers to provide, say, A and B for $12,000, C and D for $5,000. Hank comes in and offers another complex bid. You get a whole bunch more of these bids. You run your winner determination algorithm, basically a weighted set packing problem, but a very large one. And it comes back and says, well, you know, you should get A and C from Fred and B, D, and G from Frank, and so on. It's going to cost you $57,000. And then the bid taker says, but that's no good. It gives too much business to Joe. Okay? What's happening here is that the purchasers, in this case, have preferences for non-price attributes of the allocation. They don't care about minimizing cost alone, which is the focus of these combinatorial optimization algorithms, but they have preferences for non-price attributes. They might not want a particular supplier to get too much volume, for example, because of the risks associated with it. Or they might not want a supplier to get too little volume because they've got a long-term relationship with a particular incumbent. They may care about the average quality of the product that's being produced. They may not want too many winners, too many suppliers, or too few suppliers for various reasons, and so on. It's very clear that purchasers have a particular utility function in mind. Okay? The problem is they're very uncomfortable articulating precise trade-off weights. If you ask them, what would you pay to reduce the percentage volume of your business in this procurement auction or sourcing event that went to Joe by 1%, they'll say, well, maybe $500,000, but no more than 1.2 million or something like that. Okay, they have a hard time articulating with any sort of precision exactly what their preferences are and how they should be traded off against cost. All right, so those are a few examples. What I want to talk about today, and I will get back to this procurement slash sourcing example in a few minutes. I want to talk today about using the notion of minimax regret as a way of doing robust optimization under utility function uncertainty. What we'd like to do is elicit enough information about say the bid taker's preferences to be able to make a good or perhaps optimal decision on their behalf, but without completely nailing down their utility function. Okay? So I will talk about the general model that we've developed in a number of domains. I'll give you the specifics of the formulation for the sourcing example. Then move on to talk about how minimax regret can be used to drive preference elicitation, to determine what are good queries, what is the relevant information that will help us make better decisions on behalf of the particular user. And then, depending on how much time we have, I'll talk a bit about mechanism design with partial revelation. As those of you familiar with mechanism design are aware, mechanisms are basically eliciting utility functions from people, thereby facing this preference bottleneck. So we've been working recently on the design of mechanisms using partial revelation of utility function or types, using some of these minimax regret techniques to decide how best to design mechanisms. All right, so let's jump into the details here. Basic decision problem, just to set the terminology. We'll assume that we've got some multi-attribute outcome set, I'll call it X plus here, over a set of attributes X1 through Xn. I'll assume that we've just got a finite set of attributes, each with finite domains. It's not strictly necessary, but it'll ease the presentation, so to speak. We'll also have a set of constraints on the set of on this multi-attribute outcome set defining the feasible outcomes. These might be logical constraints. It might be a constraint satisfaction problem, for example. The feasible outcomes might be simply the elements in a particular product database. They might be the outcomes of some complex optimization process, as we'll see in winner determination. Feasibility can actually be very difficult to determine in some cases. We'll assume that we've got a user utility function mapping the outcome set into the reals, telling you how good or bad a particular outcome is to a particular user. Generally, this utility function will be parameterized fairly compactly, say with some weight vector W. In a lot of the work, we use linear models or additive models. I'll show you an example of that. Generalized additive models, things of that nature. Our goal then is to find an X star that maximizes the user's utility among all feasible outcomes. Okay? And generally speaking, this will require some optimization. We'll have to solve an LP, do some dynamic programming, a mixed integer program, something of that nature. Okay? Of course, that's great, classic decision problem. But of course, as we know, user preferences are often unknown. And they vary much more widely than dynamics, okay? It's very hard to predict what a particular user will want us to do, Okay? And this is basically the preference bottleneck that I've already alluded to. Okay? Our goal, one of my personal goals, is to automate the role of a decision analyst. I would love to have a decision analyst sitting on my desktop. Okay? Of course, decision analysts face very difficult questions. We know that people have a very hard time articulating their preferences with any degree of precision, certainly numerical preferences, and we're going to have to account for that. But we also have some other questions that we need to address. In particular, we want to ask, well, what preference information is relevant to the particular task at hand? I don't need to know everything about your utility function to be able to decide that this is a good decision if the feasible outcome set is fairly restricted. Second question is, when is the elicitation effort we engage in when we get some information from somebody about their preferences worth the improvement that it offers in terms of decision quality? Okay? Generally speaking, I could take a long time and impose a lot of, say, cognitive burden on a particular user to find out exactly what their preferences are, but it may not be worth the improvement that it offers me in terms of underlying decision quality. I may be able to make a good decision without knowing all of that. Okay? If we admit that, then we know that we're going to have to make decisions with partial utility function information. Okay? If that's the case, then the question naturally arises, what decision criterion should one use? Because we can't maximize expected utility, for example, if we don't have the user's utility function in hand. Okay? So I want to start with that last question. What decision criterion should one use when making decisions with incomplete objective function information or an incompletely specified utility function? So I'm going to talk today about strict utility function uncertainty. I'm going to assume that the user's utility parameters W are unknown, but that they are known to lie in some feasible set W, okay, where W, for example, is defined by a set of linear constraints on this weight vector. Okay? Where these linear constraints will come from, well, generally it'll be the outcome of some elicitation process, and we'll get into that in just a few minutes. Okay? So what we've got here is what I'll call an unquantified or strict approach to uncertainty. I assume your utility function is in this set, but no more. Okay? This is in contrast to, say, a Bayesian approach where we might have a density over the space of utility functions. Don't have any problems with Bayesian approaches. It's something that I've worked with in the past and continue to work with. But there's some advantages to looking at this strict uncertainty model. So now a key question is, if this is all I know about your utility function, how should I make a decision? Okay? What I'm going to propose is the notion of minimax regret, or I shouldn't say propose, I'm going to advocate the notion of minimax regret, which I'll define in 3 stages, and then say a few words to try to motivate or justify it. We'll say that the regret of a particular outcome X, given that the user's utility function W is simply the loss incurred by taking decision X rather than acting optimally, given the user's utility function is in fact W. Okay? So how much do you lose by not acting optimally but doing X instead? The max regret of a decision, since I don't know the user's utility function, all I know is it lies in this big set W. The maximum regret is the worst case loss, given that an adversary could select any utility function within W. Okay? So if I were to do X, an adversary could make me regret X by this much. Okay? Then we'll say that the minimax optimal decision, or the decision that minimizes maximum regret, is that decision that gives the adversary the least power in that respect. Okay? So we basically want to choose the X star that minimizes max regret in the presence of such an adversary. All right? So I hope that's fairly clear. I'm going to go over this very quickly. Why would we want to use minimax regret as opposed to other criteria that people have considered in robust optimization, like max and min? Well, obviously, we've got a certain robustness in the face of uncertainty here. Okay? In particular, if we're concerned, again, about this worst case loss, okay, then this is the right thing to do. Okay? Now, one can say, well, this is very cautious, but there are a number of reasons, which I can get into maybe later, why I still think this is a much better approach than, say, max and min. Of course, if one has priors, then of course one could be Bayesian about this and not be quite so cautious. But it turns out that even when we've got priors available, that using Minimax regret, as we'll see, can be a very effective driver of preference elicitation. Okay? Obviously, it's useful when priors are not readily available. And in our experience, it's much more tractable, actually, to do the reasoning with these strict uncertainty sets. Okay? So how does one go about computing Minimax regret? Very briefly, let's write out, this is sort of the obvious formulation in a very generic form. We basically want to min over our choice of outcome, and then let the adversary max over the choices of utility function and this adversarial outcome. The difference between the utility of the adversary's outcome under that chosen utility function and our outcome. Okay? So in terms of making sure that we can compute these things effectively and quickly, well, we've got a couple of problems. First of all, we've got a Minimax program, so we don't have a straightforward minimization, for example. We've got a quadratic objective, which is not a problem in general, but for integer programs, it's going to cause us some difficulties. So the general approach that we've been taking in many of these domains is to use Bender's decomposition. I'll explain this in a few minutes for those of you not in the math programming world. Bender's decomposition and constraint generation to break the Minimax program to convert it into a minimization. And then we use various encoding tricks to linearize these quadratic components. Okay? And of course, the details are going to depend on the specific problem or formulation. All right? We've been looking at this in the context of a number of different applications: product configuration, resource allocation, and autonomic computing. Recently been doing some work on the robust solution of Markov decision processes where we don't know the reward function precisely. What I'm going to talk about, just to give you a flavor of how these formulations work, is winner determination in combinatorial auctions in these sourcing problems. Okay? So, first, let me just, again, set the groundwork, and then I'll describe how we go about computing Minimax regret. I'm going to be talking about a reverse combinatorial auction. Setting's really quite simple. We've got a buyer who desires a collection of items G. We've got sellers who can offer bids on bundles of these items. So a bid is basically a collection of these items and a particular price with which you're willing to offer that collection. We can have a lot of various side constraints, and we can make this more expressive if we'd like, but this is sufficient for our purposes here. Feasible allocation is basically any subset of the bids that covers the buyer's needs, G. Okay? We're going to use X to denote the set of feasible allocations. And the winner determination problem is basically to find the least cost allocation that covers G. Okay? The least cost feasible allocation. Okay? But as we saw earlier, generally purchasers have preferences for non-price features. So they care about things like the number of winners, geographical diversity of their suppliers, things of that nature. So we're going to assume we have got a finite set of features, F1 through Fk, that they care about, that we've got a quasi-linear utility function. So basically have linear utility over outcomes less the cost of the allocation. Okay? We have ways of generalizing this if we've got nonlinear features or nonlinear utility for features, but this will illustrate what we need to do here. So we're going to assume the user has quasi-linear utility function, but we don't know the weights. We don't know the parameters. All we know is that it lies in some polytope W. Okay? So you write this out, and we basically have the same Minimax regret equation with where we look at the difference between the weights multiplied by the adversary's features less our features, and the difference between our costs. Okay? And we want to do this optimization. Okay? Again, Minimax and quadratic. Right? So how do we get around that? Well, first we can take that Minimax program and convert it into an integer program. Simply by minimizing over our choices, minimizing over x, the outcome that we'd like to choose, delta, which corresponds to x's max regret, subject to the constraint that delta is greater than the actual regret for any choice the adversary could make of allocation and utility function. Okay? Unfortunately, this is going to have infinitely many constraints. Two simple observations, though. Let us break that. First of all, the active constraints here can only occur at a vertex of the polytope. That should be fairly evident. Second, given a particular utility function, say W at one of the corners of this polytope, the only thing the adversary should do to make us maximize regret is to do the optimal thing at that the optimal thing for that utility function. If he does anything less, he's losing advantage relative to our choice, okay? So all we need to do then is rewrite this thing by minimizing delta subject to the constraint that it's better than the regret we would face at any corner of the polytope given that the adversary does the optimal thing at that utility function, okay? So that's great as far as it goes, but again, we don't like to enumerate vertices of polytopes and anything but something where we've got maybe 2 or 3 features. So we apply a constraint generation procedure. Again, pretty straightforward. We're going to assume, what we're going to do is basically, going back here, is solve various relaxed versions of this integer program. We'll start by throwing into a set gen a set of an arbitrary feasible allocation and an arbitrary utility function. We're going to then iteratively solve that same LP, but only with same IP, but only with the constraints, only with constraints corresponding to those in this set gen, to pairs in this set gen. At any point, we're going to get a solution to this relaxed IP. We'll call that thing X star. And it's going to have objective value delta star. Basically, this is giving us the allocation X star that has minimax regret. If we were to tie the adversary's hands and say, you're only allowed to pick utility functions and allocations in this generated set, okay? And delta star will be, the solution delta star will be the max regret against that restricted adversary, okay? But of course, we don't know if this is the minimax optimal solution because we tied the adversary's hands. So then we just untie the adversary's hands and say, all right, I'm proposing this as a solution. How much can you actually make me regret it if I untie your hands, okay? So we solve an integer program. I'll tell you about this in just a second on the next slide. We compute the max regret of X star against with respect to W. This will give us a solution. This will give us a solution. Let's call it X double primed and W double primed, which is basically the adversary's choice. The witness, the adversary, will compute to prove that the max regret of X star is in fact some value R. Okay, so this is the max regret of X star. Now, if R is greater than delta star, we know by untying the adversary's hands, he's been able to make us regret it more. So obviously, we didn't have these constraints weren't tight enough. So we're going to throw this thing into the set gen, all right, and iterate. However, if R was equal to delta star, can't be less than delta star. If it's equal to delta star, every active constraint, or all we need is actually present in the solution here. Okay, we've given the adversary no more power. We know we have the minimax optimal solution. Okay. Notice that basically what we're doing at this stage is computing the maximally violated constraint and throwing it into this IP. Okay. Now, in the interest of time, I'm not going to say anything about this computation. This is where some of the quadratic stuff comes in, and we've got to get a little clever with respect to particular formulations. All right, so this is the computing the max regret program. We end up with quadratic terms here because the adversary has to choose an allocation and a utility function, but there are various tricks that one can use to linearize this thing. So I'll skip over that. Okay. Yeah. Yeah.
About when you're doing your optimization in the restricted set.
Yeah.
Is the idea that you believe that most of the action is actually going on in some little corner of the polytope, and so you really only need to explore that area of it with respect to...
Well, I won't say that it's a little corner of the polytope, but what we'll be doing is basically slicing off good chunks of the polytope to say, well, okay, if this is all I let the adversary do, if he's only allowed to pick something in this corner, okay, then I would do something here, right? Then we untie him, and he's going to choose a different corner, all right? we're going to then compute the minimax regret when the adversary can do either of those things, right? And so basically we start slicing off various bits of the top polytope until we're basically, forced into a particular region, right? So we're not necessarily
Just
focusing.
wondering why you think you're going to drastically reduce the number of vertices you would have.
Here's why. Well, empirically we do, okay? It's a purely empirical question, okay? And it turns out that it actually does in a number of cases. This is a very small problem from CombinaToral, right? These are tiny procurement auctions or sourcing events, okay? Here it's a very simple problem. It has 6 features. I think it's got on the order of maybe 150 vertices. We actually did the enumeration. This is the number of rounds of constraint generation until convergence over 100 instances, right? It maxes at 11, okay? On average, it's around 4.5, okay? So it actually does work very, very well, okay? These are some other examples, very different domain. It's not sourcing, but it's product configuration. A very large problem, utility functions with 160 parameters. So the polytopes are huge, okay? And here we look at, as a function of, don't worry too much about the details. Here we're showing how tight the initial polytope is. What we're showing is the number of constraints that are generated, okay, a scatter plot over, again, 100 instances, okay? And we see it's on the order of 10 to 100, okay? So we actually do enumerate very few of these things in practice, okay? But it is a purely empirical question, okay? Now, the one thing I should note, you should be concerned about solution times like 19 seconds, and here, solution times ranging from 10 up to 1,000 seconds for some of these problems, okay? It turns out that this algorithm, A, because we've got IPs, so we can terminate early once the gap is sufficiently small, and B, because it's an iterative process. It turns out we can cut this thing short with approximately minimax optimal solutions, and it will do a very good job with respect to preference elicitation. And I'll show you that now because we're going to jump into preference elicitation, okay? So let me just, jump ahead. Okay, that's just to give you a flavor, but of how minimax optimization works. Now, how do we use this for preference elicitation? Basically, the question is this: we get a minimax optimal solution, given what we know about the user's utility function, may not be satisfied with the quality of the solution, right? The loss may be too great, the regret may be too great. So obviously, one way to improve quality, well, the only way to improve quality, is to get more information about the user's utility function. Okay, which will give us tighter bounds on the utility parameters, okay? The question is, which queries should we ask? We'd like to reduce regret as quickly as possible, obviously. We'd like to do it sequentially. We'd like to have an entire elicitation plan, not just do this stuff myopically. To date, unfortunately, all we have are heuristic approaches to the elicitation problem, but they do seem to work reasonably well. So let me go over these. Now, the first thing I need to say is, what are the types of queries that one can consider? I've already talked at the beginning about the many and various modes of interaction one could imagine with a particular user. I'm going to talk just about a couple of very simple query types. There are a lot more that we've played around with, but again, in the interest of time, I'll keep this brief. One very natural type of query is what are called comparison queries. You simply ask a user, do you like this outcome X better than this outcome X prime? Okay? Which a positive or negative answer will obviously impose various linear constraints on the weight space. Okay? These are nice queries in one sense. The interpretation is straightforward, not asking the user to assess anything numerical. It's a purely qualitative question. Unfortunately, these types of queries are non-local. So you're asking them to compare one outcome, possibly over a whole whack of features, to another one. Okay? We actually do have versions for, say, generalized additive utility models where we know how to ask local queries of this type as well. But it's something that's worth keeping in mind. I'm just here focusing on global comparison queries. Another type of query we might ask are bound queries, right? Start asking about bounds on specific utility parameters, okay? So we could ask about these specific weights, for example. Is this weight greater than V, yes or no, okay? Well, that's a difficult question for somebody to answer because it assumes that they can calibrate these various weights across each other. Well, in decision analysis, though, we know how to take that calibration into effect by phrasing them in terms of standard Gamble queries so that it's basically just a probabilistic assessment, not a utility assessment directly, per se. So it becomes just a preference query. Anyway, don't want to get into the details here, but suffice it to say that there are ways to get people comfortable answering those types of questions. Now, there are various elicitation strategies one could imagine, okay? An obvious one, I don't want to dwell on the details. An obvious thing to do is simply look at the gaps in these utility parameters, for example, and start slicing them in half, right? Obviously, if there are no constraints, that's the best thing that you can do, theoretically, okay? And in fact, people have been proposing this in conjoint analysis in the marketing research, in the marketing research community. There's this notion of polyhedral-based conjoint analysis for product design, for example. This type of strategy is very much like that, where we would pick the utility parameter that has the biggest span, okay, and ask the user to refine their estimate of that. Okay? Something that we've done a lot of work with, and as we'll see, actually works incredibly well when we're doing regret-based elicitation, is something we'll call the current solution strategy. The basic idea is this: if we're trying to reduce regret, what we need to do is either increase the lower bound on the utility of of our solution, right? The one that has Minimax regret, or decrease the upper bound on the utility of the adversary's solution, the witness that he's using to show us how much we regret our solution. Okay? So the current solution strategy, in many different domains, it comes in various instantiation, basically says only ask queries that involve parameters that determine the utility of one of these two configurations. Because if you don't, you're not going to reduce Minimax regret, because the adversary will still have the same upper bound on his solution and the same lower bound on our solution. Okay? So basically, that would eliminate some of the parameters from consideration, and you focus only on those that are in the active solution, so to speak. Okay? A number of other query strategies. Again, in the interest of time, I won't go through them. That can be applied in a number of different domains. The thing to note is that some of these are actually computationally easier to implement. You actually don't have to do Minimax optimization. You can do straightforward optimization to determine which parameters to ask a user about. Okay? So let me just show you, these are just some illustrative graphs, not an exhaustive suite, just to give you a sense of how these things work. Here's a simple sourcing problem, the same type of thing, 10 bidders, 500 items. I've forgotten the details now. I think it was 10 bidders, 50 items, 500 bids. And what we see, I'm blanking on exactly what the true optimal allocation value was. I think this is about this max regret level here is around 15 to 30% of the true value. So it's not that high. We knew coming in a lot about the utility function. What we see as a function of the number of interactions, that max regret drops very quickly using the current solution strategy. Furthermore, true regret, since we actually know the utility function that we're querying here, drops even more dramatically. Okay? Let's see. Our goal is not to get an optimal solution. We just want to go until max regret reaches a reasonable level. But we took 100 instances from this domain, 100 random instances, and actually have a histogram here of the number of interactions, the number of comparison queries that need to be asked until you actually make max regret 0, until you know the optimal solution. Again, for procurement, asking somebody 30 or 40 questions is not very many. Okay? Typically, they go off in a room for 6 weeks and figure out what they wanted. So, Here's a simple product configuration example, slightly different domain. The thing I want to point out is, A, that the current solution strategy along here works really quite well. It outperforms a lot of the other, all of the other strategies that we've looked at, including this theoretically motivated HLG, or have largest gap. This is a fairly large problem, large constraint satisfaction problem, utility models that have 150 parameters. So that may look like a lot of queries, but given that you have 150 utility parameters, there's actually not that many. So current solution works very well. The other thing I want to note is that this current solution 5 here is the current solution strategy where we cut off minimax regret computation after 5 seconds to make sure that we can ask a user every 5 seconds, well, what about this, what about this, what about this? And even though it's a pretty severe approximation, it actually has very little unnoticeable impact on the reduction in max regret. So even with very severe approximation, we can determine the right queries, so to speak. Okay? All right, so we have maybe 10 minutes or so. Let me just wrap up. I want to take just a few minutes and talk a little bit about mechanism design as well. But again, just to summarize where we are with preference elicitation here, the current solution strategy across a variety of domains works in the autonomic computing work that we've done, product configuration, whether it's with constraint satisfaction problems or product databases in these procurement or sourcing problems. It is by far the best elicitation strategy. What we see is that minimax regret actually is a very effective driver of preference elicitation. By focusing on that worst case loss, you're actually pinning down the user in just the right ways. Okay? Approximation has very little impact on query quality, which is very encouraging, right? Because we can't do preference elicitation unless we have real-time response. Okay? Number of other issues that I don't want to get into, but I'm happy to talk about them. There are a lot of issues surrounding the decision theoretically sound elicitation of information about utility functions so that you ensure proper calibration. Indifference or indecision on part of the user. They say, I'm not sure if I like that one better or worse. Inconsistency in responses. In fact, our elicitation strategies will never allow an inconsistent response because there's no value of information in asking somebody, do you like A better than B, where one of the right answers can actually be inconsistent. Okay? However, there are other interaction modes that we've looked at where inconsistency can arise. So how does one deal with that? Interface design, all kinds of cool problems that I and my collaborators and students are looking at. So let me take maybe 5-10 minutes and just say what all of this has to do with mechanism design. Okay? So imagine a problem of bargaining for a car. You've got this poor guy here. He's got various preferences over the possible car configurations that he might want. We also have sellers on the other side that have various costs of production. Okay? So they have their utility for particular transactions at specific prices as well. Okay? Why is this a preference elicitation problem? Well, it's pretty clear that if we want to match the buyer with the right seller and choose the right car, we have to know something about all of their preferences. Okay? This, of course, so we might, for example, want to choose the seller and car pair for this user that maximizes surplus, right? Maximizes social welfare. The difference between his value and his cost. Okay? And then we might want our system actually to help them bargain on a negotiated price as well. All right? This, of course, is just the province of mechanism design, where we want to design protocols for interacting agents that are assumed to be self-interested in such a way that some social choice function is maximized, or some social choice function is implemented. For instance, efficiency or social welfare might be our goal. Find the best match between this buyer and particular seller. Okay? Those of you familiar with mechanism design, I'm sure people here are very concerned about ad auctions, so you should all know about mechanism design. There's an incredible focus on the revelation principle, which basically says that we can restrict our attention to the design of direct incentive compatible mechanisms where the agents participating in the mechanism reveal their entire utility function to the mechanism. There are payment schemes that are involved that ensure that they reveal truthfully, et cetera, et cetera. Okay. Of course, this simply means that we're facing the preference bottleneck. If we're asking participants in some mechanism to reveal their utility function, we've got to face the preference elicitation problem. Okay? So what we've been working on, this is with a student of mine, Nat Hayafel, over the last 2 years or so, is the development of what we call partial revelation mechanisms. Basically doing mechanism design where we get users to reveal just the relevant parts of their utility function. Okay? Again, I'm going to go over this quickly, so I won't go into details. There's a long history of this, dating back to the classic work of Mountain Writer in the early 70s. And there's been a lot of action in the CS and economics community on this topic. Our focus has been related, but a little bit different. So let me jump. The stars mean I knew I wouldn't have time to go over this. So let me jump right to the heart of the matter. Again, given the basics of mechanism design, the goal is simply to have users reveal something about their utility function. It's usually called type revelation. Your type encodes the relevant private information that you have about your environment. Here, again, that's just your utility function. Partial type. We're going to generalize the notion by saying, rather than having somebody reveal their utility function or their type, they're going to reveal a partial type, which is just a subset of their types. Basically says, I'm not going to tell you what my utility function is. All I'm going to tell you is that it lies somewhere within within the subset. Okay. We'll call a one-shot direct partial revelation mechanism basically a mechanism where each agent reports a partial type. Okay. A truthful strategy. We have the same notion of a truthful strategy. Simply means that when you reveal a partial type, that your true type actually lies within that subset. And the goal is to devise a reasonable set of partial types that minimize the amount of revelation or the amount of computation required on the part of the agents or the amount of communication. While still getting good outcomes, while still maintaining appropriate incentive properties. Okay? Well, this is going to be difficult. In particular, we're generally interested in dominant strategy implementation, where it's a dominant strategy for the agents to reveal their utility function truthfully, no matter what the other agents do. There's some classic results in the economics literature by Roberts, more recent extensions by Lavie et al. That basically say, you know what, you can't do it, okay? Basically says the only social choice functions that can be implemented in dominant strategies is social welfare maximization or some variance thereof. Of course, we can't expect to maximize social welfare if we're only doing partial type revelation, because we're not going to know enough about everybody's utility function to say definitively this is the social welfare maximizing allocation. Okay? So there are various ways that we can go. What we do is actually relax the solution concept of dominant strategy implementation and hope that we get intuitive results. Okay? And here's how we do it. I won't go through the details here. What we're going to do is basically say, suppose that a set of agents revealed their partial types to lie within a particular subset. Okay, so I've got a partial type vector, the utility functions for each agent, let's call it theta. Okay. Given that we don't know what the user's true utility function is, we can use max regret to determine, minimax regret to determine a good allocation, the one that minimizes minimizes the loss with respect to social welfare if an adversary were to come along and pick everybody's type from the set that they reveal. In other words, pick their utility function consistent in a way that's consistent with what they've told me. Okay? If we do that, if we have a partial revelation mechanism where each agent reveals just a partial type, Okay? And the outcome is such that we always allocate or choose an outcome that minimizes max regret with respect to those partially revealed types. Then we'll call this a regret-based partial revelation mechanism. Okay? Now, what does that mean? Obviously, as we've said, you can't get efficiency. We can't maximize social welfare if we don't know everybody's type. But obviously, if the max regret for every partial type, okay, every partial type vector is less than epsilon, okay, then we're going to be epsilon efficient. We're going to be within epsilon of maximizing social welfare, no matter what the agents reveal, as long as they reveal truthfully. Okay, that should be fairly obvious. Of course, and this allows us to trade off efficiency or social welfare for elicitation effort, which is a nice thing. However, how do we ensure truthfulness? Okay. Very briefly, we can generalize the Groves payments, for those of you familiar with Groves schemes or Clark-Groves payment schemes. Basically, these are the payment schemes that are used in VCG. Well, we can't use Groves payments. Groves payments basically say you pay something that's independent of your type, okay, or what you report, less the social welfare realized by the other agents participating in this mechanism with respect to the outcome that I chose. Unfortunately, we don't know what the social welfare is for the other agents because we don't know their type, but if we have a selection function that picks an arbitrary type consistent with what they've revealed, okay, then this partial revelation mechanism with Groves payments will not only be epsilon efficient, but truth-telling will be an epsilon dominant strategy. In other words, no matter what anybody else does, I can gain at most epsilon by reporting something other than my true partial type. Okay. Quickly, just to wrap up, we can also generalize Clark payments as well, so that we get approximate individual rationality. And what we've got is an approach to the design of partial revelation mechanisms that allows us to trade off the amount of elicitation effort for efficiency. We're going to have to live with approximate incentive compatibility. That's an unusual notion. People don't typically propose approximate incentives. But the key to motivating this is that if this epsilon, it's not on here, if epsilon is small enough, okay, we know that computing a good lie, at least intuitively, is very, very difficult, okay, from a computational perspective. If the most that you can gain by lying, by deviating from the truth, is bounded by a small enough epsilon, even though formally we only have approximate incentive compatibility, from a practical perspective, agents will be incented to behave truthfully. Okay? Same thing with approximate rationality and so on. Okay? So these regret-based PRMs offer good scope for trading off these various considerations: elicitation effort with efficiency and incentive compatibility, as long as we can find a good set of partial types. Okay? That's the key. Right? This assumes you've got a given set of partial types. So I'm going to wrap up simply by saying that we can take some of the techniques that we've described for minimax regret elicitation and use these to design the set of partial types. Okay? I won't get into the details, but basically there are techniques like the current solution strategy that say this is exactly how I should carve up the space of utility functions among the agents participating in the mechanism. Okay? Let me skip all of this. Some very preliminary empirical results. Here, this is a 16-good bargaining problem with 8 utility parameters. Here, we're simply comparing how our design approach is a function of the number of bits of information about one's type that we ask the agents to elicit, how epsilon, which is our bound on efficiency and incentive compatibility, how it reduces. Okay? So our regret-based approach does a little bit better than sort of an arbitrary uniform-based approach. We've also done some work with, We've also done some work with, oops, I went backwards here. We've also done some work with sequential partial revelation, where you actually get a lot more power. Because you can ask somebody a question given the response that somebody else has given you, okay? And we actually get, for much larger problems, we get much better elicitation performance. We have to live with weaker theoretical guarantees. We can only get ex post incentive compatibility guarantees rather than dominant strategy, which is usual in sequential mechanisms, okay? Let me stop there and just summarize with sort of a couple of key points. With respect to partial revelation mechanisms, this is just in its infancy from our perspective. There's a lot more that needs to be done for the design of these partial types. Our techniques algorithmically are fairly crude, but I think there's a lot of encouraging progress that's been made there. We actually have an extended design framework where we can do much more than optimize for social welfare. We can optimize for arbitrary social choice functions in various ways. Okay, so just to wrap up here, where are we, right? Preference assessment, from my perspective, is a key bottleneck for a lot of AI applications, okay? The regret-based techniques that we've been developing are very encouraging. Regret seems, as I've mentioned, to be a very effective driver of elicitation. Computationally, it's much more manageable and much more tractable than a number of the Bayesian approaches that we've experimented with. In particular, the kind of computational approximations one needs to make with Bayesian techniques are going to be problematic from the mechanism design perspective if we want to maintain suitable incentive properties. There's a lot missing. Okay, obviously, again, you know, I have a grand vision of a decision analyst sitting on my desktop, and in order to do that, we've got to start looking more critically at sequential elicitation, looking at long-term elicitation plans, not just myopic ones, both from a theoretical perspective and a practical perspective. We've got to look at the right techniques for user interaction. We have been doing a little bit of that, but again, that's very much in its infancy. We have been doing some work where we exploit distributional information within these regret-based techniques, where we make allocations using Minimax regret, but we use densities or distributional information over utility functions to guide which questions we ask, since that doesn't really have an impact on robustness or the incentive properties in mechanism design. And obviously, we want to integrate these passive observations through revealed preference, revealed choice, and things of that nature, what is commonly now called in AI inverse reinforcement learning, into this whole framework that I think will address the grand challenge of preference assessment. So I'll leave it at that and see if there are any questions. Good.
Okay.
Yep.
So if you were to try to do preference assessment for a group of people, so you won't always get a preference, you'll get a sort of a group of preferences that may be conflicting.
Right.
How does that fit with this? Well,
the question is, how do you do this when you're talking about groups? When you're talking about groups of people, I've got two answers to that question. One is I don't actually haven't thought a whole lot about this problem. This is a subject of marketing research and conjoint analysis, for example. When you're doing product design, you do this kind of elicitation not for specific individuals, but you actually aggregate all of that data, okay, in various ways. We actually, in sourcing, in fact, we are implicitly doing group preference assessment, right? Because the people in charge of sourcing events, for example, it's not an individual, it's an entire team, and they're all reporting to different people. When you look at the utility for specific attributes like number of winners, Okay? You've got people in charge of logistics who want as few winners as possible. Okay? Whereas your CFO wants you to spend as little money as possible. Right? The marketing guys want you to give as much business to people in the Eastern corridor. Right? And so on and so forth. Okay? What regret lets you do, this notion of Minimax regret lets you do, is not make people commit, okay, where they don't have to, right? So in fact, what's happened is when we've played around with this with people doing sourcing, is that it seems to relieve some of those conflicts because you don't actually have to have a consensus utility function, right? If you're all comfortable with the bounds, right? You say, well, I don't know where my utility is, it's somewhere in here. And somebody else says, well, I don't know where mine is, but it's somewhere in here. And we can say, you know what? You don't have to refine it any further. As long as it's in here, this is a good decision. Then we're in good shape, okay? But this doesn't directly address, aggregate preferences. That's, it's a very difficult question. So. Peter? No?
I have a kind of philosophical question. So it seems like the whole reason you do preference solicitation is because people act irrationally. If they could just make the right decision one shot, you wouldn't need to get their preferences. So the question is, what happens if people's preferences are irrational? So say you have an agent, a decider who says, my most important preference is I never want to admit I made a mistake.
Yes.
And then you go on from there and you get into more and more trouble.
Right.
Is there a way to recover from that, or?
I mean, there are various techniques that one can use. So, in some other work that I've done, we've actually used noise models for responses to say, look, when you say you like A better than B, there's some probability that you didn't really mean it, right? So we can recover in that sense. It is true that it's well known that people can be very inconsistent when it comes to stating their preferences. There's a whole literature in decision analysis and experimental economics that addresses that. And we haven't brought that to bear on these types of techniques, not yet. Some of it's starting to filter in. So I don't have definitive answers, but it is a problem that people have talked about, okay? I would take issue with the question that the only reason we're doing this is because people are irrational, right? People can be perfectly rational and still not be able to solve these procurement problems or planning problems or things like that. They want our intelligent agents to be able to do this for them, right? But we don't know enough about what their objectives are, what their goals and trade-offs are to be able to actually do that optimization, right? So it's not so much that they're irrational, but they're computationally limited. Okay? So an important part of this is to be able to frame the questions in such a way that they can, get their heads around what it is that they actually are after, what it is they prefer or don't prefer. Okay? So we can't, getting back to the coach problem, where we're actually looking at trajectories of behavior. It's very hard for somebody to take one giant trajectory of behavior and say, I like this one better than this one. You could show them the same thing, 2 days later, and they may give you the opposite response, right? So it's really a question of framing, right? So we're looking at techniques for MDPs, for example, that will allow us to break these things up into the relevant chunks of behavior that people can actually wrap their heads around. So it doesn't quite answer your question, but yeah, kind of goes there. Sam.
So in a lot of situations, there's a fixed set of sort of baseline strategies. Like, for example, if I'm talking about classification, I might not know what the optimal classifier is, but I might have some experts. Or if I'm talking about portfolios, I might not know what the optimal investment strategy is, but I might have some fixed baskets. And then it's interesting to show that any particular algorithm has some bounded regret with respect to retrospectively picking the best of the competitors' baselines. So let's say I gave you some baseline allocations, right? There are guys inside the company who say, I don't know about all this fancy preference elicitation, blah, 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 but I propose the competitor X sub 0. That's a baseline. So is there something you can say about, if you follow this particular Minimax elicitation strategy, you'll do no worse than clairvoyantly having picked the best from this list of baseline allocations? Like, I mean, it's a bit.
That's, yeah, I'm trying to get my head around this notion of a baseline allocation, say, in this setting, right? So, look, clearly there are various rules of thumb that people use, okay? So let me tell you how standard practice is once you've got sophisticated optimization techniques, right? The way people actually do this, so we haven't deployed this preference elicitation technique with clients yet. They've seen it kind of in demo mode, right? They're pushing us on this. But the way people actually do allocation in these sourcing events is to basically say, look, get me the least cost allocation, right? I don't like this. Let's redo it with a constraint. So don't give this much business to Joe. Price shoots up. They say, well, I didn't mean that as a constraint. Let me put in a different constraint. And they go on and on. They'll generate what are called what are called scenarios, and often hundreds or thousands of these things. They'll eyeball them all and say, I like that one, okay? That does immeasurably better than any baseline heuristics that people have used. Nobody who's done sourcing this way has said, you know what, my rules of thumb do better, right? I mean, that's about the only response, that I could give, okay? What we're trying to do is basically automate this technique, right? So. Okay. Thanks.